This video will be a quick review of Quiz 1 answers. Questions 1 through 10 were multiple choice. Please refer to your quiz. Question number 1 was increasing the sensitivity of an instrument and the effects that will have. The important effect of increasing the sensitivity as listed in the multiple choice is it will decrease the limits to detection. A decrease in limits to detection is actually an improvement on how low you can go. Increasing the concentration, on the other hand, in question 2 has no effect on sensitivity or resolution. None of the above. Increasing the path length of an instrument, B, will result in an increase in the sensitivity and therefore, like question 1, will decrease limits to detection. Doubling the wavelength, making a longer wavelength, means lower energy. That halves the energy. An increase in the random noise of an instrument has no effect on sensitivity, but it will increase the limits to detection. The reason you decrease the slit width W is to increase resolution. I would like to point out that an increase in resolution results in a decrease in the sensitivity because as you tighten the slit, you let less of the signal through. So even though you are improving the resolution, you are decreasing the amount of signal and so therefore reducing the sensitivity. It is a trade-off. Increasing path length B repetitively is done to increase the sensitivity. Increasing the focal length so if the angle stays the same, as you increase the focal length, you increase the spread and therefore increase resolution, decrease sensitivity. Decreasing the linear reciprocal dispersion also increases the dispersion, so we are increasing resolution and again decreasing sensitivity. Using absorbance versus fluorescence certainly does not provide increased sensitivity. Fluorescence has the advantage in sensitivity and selectivity, but this will result in an increase in dynamic range. Questions 11, 12, and 13 are calculation questions. D to the minus 1 is the slit width D, that is the fraction grating slit width divided by the n focal length. In this problem, there were 1200 gratings per millimeter, which means if we take the reciprocal of 1200 and convert to nanometers, that means that D is 833 nanometers. The focal length is simply 197 millimeters in this particular problem, giving us an answer of 4.2 nanometers per millimeter. The correct answer for these set of numbers would be 4.2. Given a D to the minus 1 of 2.5, calculate the bandwidth delta lambda. We are not trying to resolve two peaks, we are simply calculating bandwidth. That is WD to the minus 1. Multiply those two numbers in this particular case. I get 2.5 times 2.6, I get 6.5. In this problem, we have the total absorbance at 440 is equal to 1.165 at 440. That will be the combination of the sensitivity of the chromate, just designated by C, plus the sensitivity and absorbance of the permanganate. We will designate the concentrations of the chromate solution as Cr and the concentrations of the permanganate as just Mn. The total absorbance at 660, which was 1.470, is equal to the absorbance of the chromate solution, 0.105, its sensitivity, times its concentration, plus 0. That actually makes our life somewhat easier. That means, using this equation, we really can solve for the chromate concentration simply dividing both sides by 0.105. The chromate concentration is 14 ppm. Once we have that, we can simply substitute that back into the first equation because we now know that the concentration of the chromate is 14 ppm. Times 0.0842 times the concentration of the permanganate. If we solve this, I can multiply these two by each other, divide both sides. .8 ppm is the final answer.